Good morning, good afternoon, or good evening, wherever you are in the world. Thank you so much for joining us today. My name is Joy Bastaros, and I'm going to be your webinar host for the day, coming to you from Houston, Texas. I'd like to welcome you to today's webinar. Our topic for the day is how to overcome the challenges in electric vehicle embedded software development. A little bit about today's speaker. We have with us today Lakshmi Narayan. He is an senior technical product engineer here at Siemens Digital Industry Software. He's an automotive enthusiast. He's well informed with the latest automotive trends and the upcoming technologies. He started his career as a software developer in the infotainment systems for renowned brands and has the expertise in providing software solutions for remote and semi-autonomous systems. In his 12 years of experience in the automotive domain, he has worn many different hats from software development to integration and testing. Currently, he works here as a senior technical product engineer, as I stated, and works closely with customers to understand and provide on-site support and solutions, generating ideas and new features into the product in his focus area. We are very happy to have you with us today, Lakshmi. And with that, I'll go ahead and turn it over to you to get us started.
Hello, welcome to today's webinar on how to overcome the challenges in electric vehicle embedded software development. I am Lakshmi Narayanan. I will be your today's presenter. Let us take a look at the agenda. I have divided the webinar into 4 sections. Section 1, Trends and Overview of Powertrain Systems. Here we will learn about current electric vehicle trends and later move to overview of powertrain systems. They are comprising electronic control units, ECU, and functionalities to better understand the challenges and the possible solution. Section 2, we will look into 4 different challenges faced in software development. Section 3, we will see how to overcome each of those challenges. At the end, we will summarize today's learning. Trends and overview of powertrain systems. At Siemens, we consider that vehicle electrification is a driving force in the ongoing revolution in the automotive industry. Electrification is one of the mega trends in the automotive industry, moving from a few models to several models. This trend is primarily driven by the following factors: legislation, people's interest towards sustainability. According to IEA, in fact, during pandemic, electric vehicles are one of the few technologies on track under the sustainable development scenario. Latest development in the direction of battery systems and other EV components, making them more affordable and almost same price tag as ICE. Growing charging infrastructure across the globe. There are at least 1 million public chargers available. EV share of new cars sold would be 28% by 2030 and will reach 58% by 2040. This is driven by factors like automakers who entice the customers with wide menu including electric SUVs and committed to increase the offer. Let us look into a trend that is more specific to automotive electric drive, combining or integrating functionalities to reduce the cost by integrating the hardware and thermal management system. There is another trend. Plug and charge will be a new norm. Driver has to just plug the charger and relax. EV communicates with the charging station for payment and authentication without having to use a RFID and a card for payment. Electrified powertrain. Electrified powertrain consists of 6 ECU, mainly DC-DC converter, monitors and controls DC-DC conversion of high voltage to an auxiliary 12 volt battery or the standard battery, inverter, monitors and controls DC to AC for running electric motor from DC high voltage battery, e-machine or e-motor, monitor and control of motor driving phase currents and torque application, charge control. This issue is country or technology specific with a dedicated protocol for orchestrating the charging process and communicating with charging station or electric vehicle supply equipment EVSE, onboard charger or OBC, monitors and controls charging process during AC charging, battery management system or BMS, monitors condition health of the high voltage battery. It monitors multiple parameters like total voltage, voltage individual cell, state of charge, state of health, etc. Challenges in EV embedded software development. Today we will discuss about 4 main challenges. Architectural. With new EV vehicle architecture brings new challenges. These architectures contain more power electronics which poses new challenges in architectural design of the ECU itself. All cars on the road has to be secure and safe. EV has some concern with respect to high voltage battery and the charging. Charging protocols. Different charger needs different communication protocol standards. Let's dig deeper into this topic to understand more. Architectural challenges. As we have seen in the section trends, one of the trends is integration of functionalities. It is known as EV combo box architecture. Integrates 2 EV functions into a single ECU. Why is it required? To simplify the wiring, combining cooling system, mechanical housing and control system. Combo box can be implemented in multiple ways. I have listed a few of them here. OBC plus DC-DC converter, OBC plus an inverter, inverter plus a DC-DC converter. In some cases, architecture may require functions in different ASIL like OBC in ASIL B and inverter in ASIL D. It is possible to develop a EV combo box without a multi-core solution, but it would be good to have them in a multi-core environment. In case if one of the EV function has to be fail-safe or to improve the performance later. Requirements one would need to support this architecture: a microcontroller and an AUTOSAR stack with multi-core support. AUTOSAR BSWs as ASIL qualified in case if the functions has to be fail-safe. Security challenges. Current generation vehicles are increasingly connected. They contain a highly sophisticated electrical and electronics architecture with a large number of entry points like diagnostic ports, USB, Wi-Fi, etc. EVs will have an additional entry point, the charging port, for charging the vehicle. This will be connected to EVSE or the charging station. Not to miss, in the recent months, we have seen cyber attack on the public infrastructure for ransom. What are the possible attacks and their consequence? Data loss. Hacking the vehicle with exposed interface could lead to loss of personal information or payment information. A compromised charger could inject ransomware or a Trojan horse to take control of the vehicle. Damage to the battery pack by hacking into the vehicle and could incur a huge loss. Compromised EV could transfer the risk to another EV or to EVSE and back to the grid network. Charge control mainly and BMS in some cases, which require to communicate with the charging station for authentication and payment purposes. These ECUs needs to be protected against the threats. What are the requirements to overcome these challenges? A firewall to protect the vehicle network, TLS, transport layer security, SECOSI, secure onboard communication for secure communication. We will discuss about this in the subsequent slides. Hardware security module. Safety challenges. Safety is a major requirement for manufacturers. The introduction of high voltage components in EVs add more safety requirements into the system. Let us take battery management system or BMS. Its main goal is to keep the battery healthy by monitoring parameters such as state of charge, state of health, etc. and taking required actions to keep the battery functionally safe. High voltage battery operates effectively in a specified range of voltage and temperature. The range is based on the battery type and the system design. If a cell temperature goes outside its intended range or over, it will be needed for the BMS to take action, maybe even cut off or isolate the cells or battery. BMS is packed with full of fail-safe functions. Another example, inverter, which also requires to satisfy functional safety standards. Since inverter converts DC to AC, which in turn drives the e-motor, determining the vehicle speed. Failing to do this correctly could result in unintended behavior such as unintended acceleration. BMS and inverter contain functions which have a functional safety impact and thus need to consider appropriate ASIL requirements in their architecture and design. To satisfy a requirement as ASIL qualified, all the interacting modules or the components has to qualify with the same ASIL or higher. And quick safety qualification is required as well to be ahead in the market. Requirement to overcome the safety challenge to have a AUTOSAR BSWs as ASIL qualified. Challenges in charging protocol. EV PHV are well established on the market. Chargers and charging technology are still evolving. On the right, you could see different vehicle plugs or chargers available now. Type 1 J1772, also known as J-plug, and Type 2, also known as Menikis. These two are mainly used in North America and the EU. CHAdeMO is a DC fast charging developed by 5 major Japanese automakers, mainly used in Japan, EU and North America. Combined charging system Type 1 and Type 2 or extension of Type 1 and Type 2 with an additional port for DC charging. GBT used in China. In recent month, China Electricity Council and CHAdeMO started to work together and merge the CHAdeMO and GBT to a new CHAoG. Superchargers developed and used by Tesla, also known as Tesla superchargers, can be used for both AC and DC charging. Multiple standardizations are ongoing based on national international level. For example, CCS Type 2 across the EU. Physical connector level, for example, CHAO-G is in progress. On communication protocol level, for example, ISO 15118 used in CCS. Requirement to face this challenge is to have a communication stack required for specific protocol standard. Every challenge can be transformed into opportunities. Let us see how can we overcome these challenges. Electric vehicles require an integrated development approach to solve the complex challenges. I would like to present here overview of capital W systems development flow. The first stage is identifying the requirements and carrying out multi-domain system modeling covering mechanical, electrical, electronics, software, etc. Once the multi-domain model is complete, we can extract the ECU aspects. The first arm of the flow covers software network development. Capital delivers a solution to drive a full embedded software flow through to software running on ECUs. The first step after the WE system definition stage is to develop a software component and architectural design using Capital Software Designer. This then can be fed into Capital networks to design, analyze, and verify the in-vehicle communication networks before again flowing through to the embedded software implementation stage, where the embedded software is designed and configured for target ECUs using AutoSAR tools such as Capital vStar Integrator and verified virtually with Capital vStar Virtualizer. The second arm of the flow covers electrical system design, harness manufacturing engineering, and in-service publication creation. This is where the electrical distribution system is designed both logically and physically, verified by correct by construction methods, and prepared for manufacture. The manufacturing of electrical harness is hugely complex, and Capital provides solution to optimize that process of product into service. Customer then would need able to efficiently service, diagnose, and repair the electrical systems, and Capital provides solution to make that process far more efficient. Capital is data centric and built upon data and process backbone to enable extremely high level of automation, data coherency, and integration with adjacent domains such as mechanical design. This W data management system enables traceability, change, and configuration management that customer demand. All through the development process and into the service, Capital enables continuous verification. The W systems are a wider part of life cycle within the organizations. We provide deep integration into PLM systems such as Team Center and other necessary domains throughout the product development process. With exploding complexity of W systems, development happens in the context of model-based systems engineering or MBSE. To deliver this, we integrate into other domains to deliver a truly integrated system development, including MCAD, PLM, and ALM systems. Advanced integrated W systems development tools are required today to deliver tomorrow's advanced product in automotive, aerospace, and industrial. Before we move to Capital vStar solution, I would like to give an overview of one of the AutoSAR concept, layered software architecture. As you might have known, AutoSAR is the dominant standard for automotive software. All the major OEMs and most Tier 1 suppliers are involved. It includes a development process, abstraction from hardware and application, and the complete software middleware. Let us have a look into the layered software architecture. Between application software component or SWC and the microcontroller, AutoSAR can be considered as 5 layers. AutoSAR runtime environment or RTE separates the application from lower layers. By this, it is making sure the reuse of application so that application can be used for several variants. Service layer provides services like system services, OS, ECU mode management for enabling ECU functionalities. ECU abstraction layer, mainly communication stack and trans receivers, makes the upper layer independent of ECU hardware layout. Microcontroller abstraction layer or MCAL, often provided by MCU vendor, direct access to make best use of MCU functionalities, abstract all the details of MCU to the upper layers. Complex drivers, direct interaction from RTE to hardware. This is mainly needed for OEM specific functionalities to access extra features in the MCU, or in some cases if the feature is not supported by AutoSAR. These layers are highly configurable and sometimes optional. Middleware components are used to deliver the functions of basic software. Components in these layers are common to all the users, but configurable to suit the requirement of OEM, considering the application functions and hardware of the ECU. Capital V Star Multicore Solution. Capital V Star Multicore Solution helps to realize EV combo box architecture by distributing the functions across multiple core. Let us take an example. EV combo box OBC DC-DC converter. Place OBC in core 0 and DC-DC in core 1. In feature, if one of them needs to be fail-safe, it is easy to do so. Multi-core solution can be applied in two different use cases, performance and safety use case. As name stands for itself, performance use case is to distribute the software to improve the performance. Let's say you have high CPU load due to communication of CAN and Ethernet. With COM split, each core could have single COM module and thereby reducing the CPU load. To avoid any overheads like inter-core communication, all the SWCs, MCAL and other relevant modules are moved to the same core. Looking at the safety use case, software partitioning based on safety level. Continuing from above example, let's say OBC in core 0 has to be ASIL B qualified. Above architecture holds good and one would need ASIL qualified modules with minimal effort on integration. Finally, but importantly, master satellite concept, which is required in a few cases. Let's say a DEM module for error reporting. Both OBC and DC-DC converter would need to report errors on any malfunctioning. Using a master in core 0 and satellite in other cores, satellite will update the status to master on request or based on the updates. Capital V Star Security. Capital V Star Security provides a wide range of solution against cyber attack, since threats can be from within vehicle network, from the internet, external infrastructure and even the whole network could be hacked. Capital V Star implements multi-layered embedded security for easy use in a connected vehicle, starting from ECU level, in-vehicle communication, architecture, and vehicle connectivity. It provides features for integrity, authenticity, and confidentiality. Let us take a look into different solutions to handle the security threats. Standardized security components. AutoSAR CryptoStack. CryptoStack does not provide a security concept. It offers cryptographic services that can be used to support and realize a certain security concepts. Vehicle intrusion protection. Firewall. Firewall, which is not specified by AutoSAR, while we support in our portfolio. For a firewall, early detection is the key, and open ports needs to be blocked to avoid being exploited by the hackers. Data transmission integrity. Secure onboard communication, which is abbreviated as SecOC. It's a part of AutoSAR concept used in secure in-vehicle communication. It adds or processes security relevant information. Transport layer security, or TLS. It's a cryptographic protocol that provides end-to-end communication security over networks. To enable TLS support in vStar, we rely on a third-party solution which is proven and used for a large customer base. Integration of third-party solution with capital vStar is under development. Hardware provided security features and acceleration. HSM, a vital security element which is still missing in AutoSAR. Capital vStar HSM implementation provides onboard security cryptographic operation, encryption, hash and integrity verification, and digital signature functions. If you are interested in cybersecurity topics, please do check our webinars on cybersecurity. Capital vStar functional safety. As we have seen in section challenges, BMS has to be fail-safe to ensure the safety of EV itself. BMS might require to satisfy ASIL D. To make it ASIL D, all the modules in the partition needs to be ASIL D qualified. Capital vStar safety can be used for all ISO 26262 defined levels, that is, development of any systems with functional safety standards from ASIL A to ASIL D. Capital vStar supports mixed ASIL software partitioning in the system. This is really important feature to remove any limitation of implementing EV combo box, since there is a higher possibility that either of the function could be in different ASIL. vStar safety implementation works efficiently in both single and multi-core microcontrollers. Last but not least, capital vStar functional safety also helps in EC integration and provides complete set of documentation for safety compliance. Charging protocol communication support. Chargers follow different charging protocol standards. We will see 3 of them here. IEC 61851 used in CHAdeMO and CCS for basic signaling. It is based on can be realized by integrating with capital vStar CAN stack. GBT 27930 is a Chinese standard for charging. It's based on J139. Can be realized by integrating with capital vStar J139. ISO 15118 used in CCS for high-level communication during the DC or fast charging. Current offering from Siemens is a TCP IP stack from a partner which is in progress. Summary. Let us summarize today's webinar. We have seen 4 challenges: architectural challenges, EV combo box architecture, which integrates 2 EV functions into a single ECU. Security challenges. A new entry point for charging increases the risk of cyber threats. Communication with the charging station needs to be secure. Safety challenges. ASIL qualified components to support safety requirements. Charging protocol. Different charging protocol standard requires distinct communication. IEC 61851 requires CAN, whereas ISO 15118 requires TCP/IP. Capital V Star solutions. Capital V Star is well suited for ECU consolidation with the following solutions: multi-core solution to enable software or function distribution across multiple cores and build a combo box architecture. Security solution, a layered approach to protect EV in a connected environment. It provides secure in-vehicle and vehicle-to-grid communication. Safety solution, functions in BMS and inverter requires to be functionally safe. With AUTOSAR BSWs as ASIL qualified helps in fast deployment of functional safety requirements. With capital V Star communication stack, it is possible to be quickly adapt to new charging protocols. Thank you for your attention and your time. I hope you found the webinar informative and it provided you some insights into the challenges in the EV embedded software development.
And with that, this officially concludes today's webinar. Thank you so much for joining us and have a great day.